Okay, well, good afternoon. Welcome to this session of the SICSA Conference 2020. You're in session 4 Beyond Computational Chemistry, which is brought to you by ScotCHEM, the research pool for chemistry, and SICSA. And we've done this as part of our initiatives on research innovation in Scotland to bring disciplines together where maybe some of the interactions are not necessarily obvious to everyone. We're happy to have in the session two great talks, one by Professor Leroy or Lee Cronin and by Dr. Thomas Label from the Universities of Glasgow and St Andrews. And first of all, we'll introduce Lee. So Lee is Regius Professor of Chemistry at Glasgow. He has a quite extensive research group of about 60 people who are scientists, who are not just standard chemists, as some might expect. His research interests are very broad, going from artificial life, the inception of biology through inorganic chemistry, digitization of chemistry, artificial intelligence chemistry, and generally the complexity and information that is contained within chemistry. So I'll let him give his talk now, and then we'll introduce Thomas afterwards, and we'll have our Q&A after all. Just want to finish with a quote from the bio that Lee sent us, saying nothing is impossible until it's tried. I actually quite like that sentence, so I'll let you lead with that, Lee.
Thanks. I'll share my. Thanks, Alan. I'm now going to share my screen. Hopefully, you can see the main slide. Is that correct? Can you see it?
Yeah, it's perfect.
Okay, great. So yeah, that's a very succinct intro, and I'm actually going to talk about all those things today, really in the context of new horizons in computational chemistry. I'm not a computational chemist, but I don't know what I am in that regard. I mean, I built my first functioning computer when I was 9, using household parts, perfectly functioning washing machines and telephones and things. And then I got a chemistry set and a ZX81 a couple of years later, and I guess I've been trying to fuse a few together. This kind of GIF, can you see the animated GIF? So the animated GIF is just showing a kind of my version of what it's like to fly through chemical space to kind of find out what molecules exist. And one of the problems that we have with computational chemistry is it's possible to enumerate chemical space, but that's really a virtual mathematical space. And we want to kind of figure out what actually exists. As Alan said, I have fairly wide-ranging interests, but they really are centered on 4 things. My group really does 4 things. We want to understand if we can make a new form of life from chemistry. And then in the process of making new life forms, we realized we could digitize chemistry, that is, control the synthesis of molecules using robotics and computational techniques. And then if we can use computers to control chemistry, could we use chemistry to do computation? And that's another strand that I won't be talking about today, but another strand that I'm developing. In fact, I'm just building a supercomputer that's based upon chemical switches, not molecular switches, but more like a chemical brain. And all this is about this idea of this transition to information and this question of how does a random chemical system become information processing? This is the question I want to answer. It may seem esoteric, but in the answer to this question, there are some important things, whether aliens exist, how easy it will be to make a new origin of life, a new life form, and also how to crack open the current concepts of limiting drug discovery. I hope you could see those movies and everything on my slides working. Is that okay? Just so I can get maybe a thumbs up from someone in the audience. So I'm not talking into a void.
Sorry, everything's going well.
Thank you. So, okay, so what I'm going to talk about in the next half an hour is just I'm going to talk about 3 things principally. I'm going to talk about a new way of thinking about molecular complexity and to therefore search chemical space. I would say that this talk, everything here pretty much, apart from the computer, which I published last year, I think it was in Science, everything I'm talking about today is unpublished. There's another paper coming out later today, but until the embargo breaks at 6 p.m, I can't really say where that is. But the second part of the synopsis is to talk about how we are digitizing chemistry and how this is a universal paradigm and how I've made it universal. Lots of people talk about digitization and doing chemistry robotically, but I'm afraid a lot of what has been done until now has not been uniform or standardized. And that may seem trivial, but the lack of standardization has meant that really we can't effectively digitize chemical space. And then finally, once we've got this new complexity measure and a new way to actually do chemistry automatically in these ChemPUs, I'm going to explain how we explore chemical space for discovery, then design, and then how we search for reactivity-driven processes and add new information. So these are three really different things you won't have heard before, not published. I could be smoking something or making it all up, but hopefully that won't be the case. I will convince you during the next few minutes that there is something to this. So before we do that, I want to just get you in the right headspace. So I've got this question. I'm going to put up some pictures, and I'm going to ask you to think to yourself, are they designed or discovered? So this is the famous face on Mars. Was this discovered or designed? A snowflake, discovered or designed? You don't need to answer, I'll tell you. The face on Mars obviously was discovered. It wasn't designed. We don't think there's any Martian. We think it was our natural weathering process produced it. Snowflake, discovered by science, produced by physics and reality, giving you nice hexagonal symmetry. No design there, unless you say that God is a physicist and designed the snowflake. This molecular wheel, well, it was discovered by Achim Müller in the laboratory. This silicon chip, I don't know what type of chip it is, but it's in a nice glowy board. Well, that was obviously designed probably by Intel, AMD, or maybe even ARM. This protein, was this protein designed or discovered? Very interesting question there. Well, it certainly was discovered, and it didn't randomly occur, the process of evolution. So something intermediate happened. So you've got designed, discovered, and evolved. Hexagonal perovskite. Well, discovered, but the ones that are now put into solar photovoltaics obviously are designed, or at least the compositional space is explored, and people were trying to go for that. The sandcastle, designed or discovered? Designed. This virus evolved. Maybe not discovered in entirely its own, but maybe designed by biology. The Saturn V rocket, designed. And so I can just give a whole load here for all of these. But now I've got them all up, I think that it's very clear the 747 is designed, as is the Saturn rocket. This molecule 124, which was made by coupling these molecules 122 and 115, was it designed? Yes. A human chemist thought about that molecule and went about making it. If it wasn't for the chemist, they wouldn't have made that. Morphine was evolved, and all the other biological parts were evolved. Now, by extension, because the 747 was made by a human being, and the human being was kind of produced by evolution, you could say the 747 was evolved, but I think that's not useful. I think it's more useful to say that humans were designers. And I'll come to this in a minute. That's a really important meaning for this kind of context of where we're going in this computational chemistry space. So this is kind of brings me to the first part of how we're going to explore chemical space, is that complex molecules are not spontaneous. If you go and look in the environment for complex molecules, I'll build up a molecule here in parts. You can probably guess that this molecule, when I finish with this molecular weight and this formula, this is actually Taxol. So this molecule, if you think about it, has 47, 48, 62 non-hydrogen heavy atoms. So to make Taxol, you have to precisely place 62 heavy atoms in a three-dimensional space and connect them together with bonds to give this exact formula with the 51 hydrogen atoms. There's quite complex ways of making Taxol in the laboratory, but if you imagine the Taxol itself is so complex, you couldn't possibly imagine stumbling across Taxol on Venus or Mars. Taxol, in terms of the space of molecules, is very special indeed. It was made by biology. A genetic system controlled the enzymes that went through a reaction cascade that biosynthesized Taxol as a secondary metabolite, a natural product. So if you find enough Taxol to measure anywhere in our solar system, not on Earth, then you have to be curious about whether there's life there or not. And that's a really important argument. But the other thing I want to say here is that now that I'm going to introduce to you today a couple of really important new concepts that are actionable for the way we do computational chemistry and drug discovery. The point is that intrinsic molecular complexity is quantifiable. This is my hypothesis. Let me prove it to you. So it's not often a chemist comes up with a new theory of complexity. And this theory of complexity, I think, will replace information in entropy, which is a pretty bold claim, given that I invented it myself. Actually, I invented the theory on my own a few years ago. And the idea is that we can look at complexity using entropy, which just tells us about the probability of a certain bit being one way or the other, or a coin flip being a heads or a tails, or look at the Kolmogorov complexity, and that is producing the computer program that produces the smallest computer program which produces the thing that you see. But what we've been developing is a thing called assembly theory, which basically asks us, when you take a number of different molecules, which molecule is more complicated by virtue of the number of different parts you can break it into. So let me say that again, that you can compare the complexity of the molecule by the number of parts that each molecule has. And so the idea is that molecules that assemble each other require information. And entropy doesn't tell you about the information you have, it just tells you about the information you lost. So really we want to go from disorder and complexity to assembly. And the way of looking at pathway assembly is really, if you look at these blocks and add them together, you can take 1, 2, 3, 4, 5, 6 steps and make this relatively complex composite. Or you can take these letters and form abracadabra in 1, 2, 3, 4, 5, 6, 7, 8 steps, which is less than the number of letters there are in the word. So that means that you can literally build things in steps once you have a pathway that has the building blocks and the information, a bit like a memory associated with the pathway. You can apply this to chemical informatics to look at the shortest route to making molecules, and also develop a model where you're moving down a binomial tree and looking at the path probability of making certain molecule. And what this graph here says that if you're to make a molecule in this number of steps, so assembly index, this is the number of steps you need to take the molecule, this is the probability that you can make the molecule in a random ensemble, okay? And you can see as the number of steps goes up, you go down and down and down, even if you change the kinetic parameter, the predisposition, if you like, the kinetics getting you to the molecule you fancy. And just when you go between 15 and 20 steps, the chances of you making a molecule, the probability space of the molecule populated with molecules comprising 15 steps or more is literally 10 to the, a mole, 10 to the 20, 10 to the 23. So that means that basically there are 10 to the 23 other molecules that take 15 steps on the same graph trajectory, which is mind-blowing. But basically what I'm saying is this is a probabilistic way of describing the likelihood of making complex molecules in chemical space. But let's actually look at chemical space. So what we did is we started to take chemistry that we knew, amino acids like asparagine, tryptophan, penicillin, ATP, and you can see that this is the assembly number, the molecular assembly number written here, and we're looking at the subunits on the scale as a function of the molecular weight of the target structure. And I'm just very careful trying to show you how these assembly motifs get built in, and probably the ATP one is the most informative. See how I've got this dinitrogen moiety, then we build up another moiety, and this is kind of the number of steps you take on a graph. This has got nothing to do with synthesis, it's just about probability. But let's actually look at chemical space for real, and we find that molecular weight in MA track to about 200 molecular weight, and then it opens up vastly. So that means that above molecular weight of 200, lots of different complexities of molecules are possible using this theory. But can we measure it? Okay, can we actually measure molecular complexity and get an intrinsic way of determining it? And the answer is yes, and it's using mass spectrometry in the first instance. And what we basically were able to show is that when you do mass spec, the mass spec and you fragment the parent molecule, the number of fragments you get from the fragmentation maps with the assembly number with this type of correlation. You can see there's a fairly wide spread, but basically the larger the number of fragments, the more complex the molecule. And this is a really quite nice finding. So we then went forward and said, right, well, can we then prove this with other techniques? We were able to do this with infrared and also with NMR. And so we've been developing an assembly technique that basically you just take a function of the number of NMR resonances you see in the proton and carbon. And of course, that can then act as a function of the number of different parts you have in the molecule. This should be pretty obvious to you if you're a chemist and you understand NMR and you use it. But it's kind of neat because it shows that we can start to now measure the complexity of a molecule without knowing anything about it. And why have we been doing this? Well, we want to start searching chemical space, doing random reactions, looking around the planet, looking in the in biology to find those molecules that have assembly numbers and asking, why have they been built? Because if the assembly number is evidence of information, that means biology must have conserved that pathway for some reason. And that's one of our working theories to explore chemical space. And what we're doing in the lab at the moment is building robots to brute force the origin of life, to basically go from a simple soup and use assembly number as a way to search for an ever-increasing chemical space. Okay, so this is part one of the talk done. I've told you that there's this thing called molecular complexity, we can measure it, but now what we want to do is start to look at how we can make a chemical processing unit to search chemical space ultimately and make chemicals. To do that, I want to make a connection between the abstraction of chemistry, this retrosynthetic analysis that existed for maybe, a very long time now, since Woodward and Corey, that you could take do retrosynthetic analysis on a product, on a target, and go backwards and say, right, this is how I'm going to make the molecule. But the problem is the human being does this and does this exclusively on their own. There is no universal instantiation in a physical system. That means you can't go from this to a robot making this molecule. The human being has to guess and use a lot of expert knowledge which isn't written down. This lack of standardization, this lack of clarity in programming, I would say, is a big problem in chemistry, and a problem that maybe we don't accept exists, actually. So what we wanted to do is make a chemical von Neumann computer, and that is to be able to take a written procedure, see how the user interprets it, designs the experiment, gets a result, and updates it. Can we somehow make this more formal? Because we make it more formal, then it's going to become more reliable, and perhaps we could even get to a point where the human being may not even need to do the procedure more than once just to validate it. So our idea is to basically digitize it and take a procedural code, make a hardware graph, compile and execute, and then have a concrete program, one molecule, one program. And that's the idea, to have a kind of chemical Spotify. Where in Spotify you get your favorite music and you play it. Wouldn't it be great to have a Chemify where you could basically get the code for the molecule and run it on your robot and have the molecule, rather than see the molecule published in Nature or wherever your favorite journal is and try and spend a few months reproducing it. Which, and a lot of people familiar with the problem would agree that your ability to reproduce the molecule is a function of, one, whether the literature is correct, two, your expertise level, and three, the intrinsic stochasticity or error proneness of the processes to work flawlessly each time, because there are, errors do crop in. So what we wanted to do is make a robotic architecture based upon von Neumann type machine, where we have a physical memory and a digital memory to making the computer, what we call it. And the computer looks like this. We designed it to basically have modules that work in batch. Batch is important because that means our chemical processing unit, our CPU, has well-defined instructions, and that we can control the batch using pumps and valves to very precisely do what we want. And what we're showing here is a computer working, moving reagents around and doing a bunch of chemical reactions. And for chemistry, in our abstraction level, there are only 4 things you need to do. You need to do the reaction, do the workup, do the purification and the isolation. And then you can then go around in a cycle and make quite complex molecules. And when we published this in Science last year, and this is the only reference to a published paper, we published the synthesis of the compounds nitol, sleeping drug, rutheniumide, which is an anti-seizure med, and sildenafil, which is Viagra. And the number of lines of code we used, the operation, the time, and the yield. And the lines of code are interesting because the only thing we needed to do differently is load in the program, and this robot made all 3 compounds, but with no physical reconfiguration. The chemist needed to do no manual labor. We've also made a whole bunch of other modules: photochemistry, redox, bioreactor, solid optimization system, high throughput, microfluidic, chiral. In fact, I'm allowed to say, it's out of embargo, that I just got some money from the UK Space Agency to make a CPU, a chemical processing unit, which is going to go into low Earth orbit and then onto the ISS, and then hopefully onto Mars with SpaceX to basically make drugs, because that's the only way you're going to get access to drugs if humans go to Mars, is via a digital chemical robot, and we have one. So these are all the different modules we've been building in our group. Notice we're not buying shiny robots. And that's not because, well, obviously we're academics and we don't have a huge amount of money, but it's not about money, it's about designing the workflow to meet your intellectual scientific needs. Lots of people are very good at producing shiny robots that aren't programmable. And what I do in my lab is I can architect the robot in my head and then I go build it. So everything you see here is hand built by my group. Obviously the NMR machine you see here on the top left, in the bottom, and this is mass spec, we buy, the rotary evaporator we buy, and the overhead stirrers. But the pumps and the valves, actually we build in my group. We've done the electronics ourselves. Here, the hardware framing we build, all the plasticware we 3D print, all the electronics controlling the I/O is built as well. I designed it initially because I wanted to have total control over the system. So, can we university program chemistry? What can we do? Well, what I wanted to do is, if we've got a robot that basically can act on instructions, can we also take the literature and turn the chemical literature into a series of instructions for the robot? Well, the answer is yes. We have a synthesis interpreter, which basically reads the literature, breaks it into operations and a graph, and then instantiates it in a robot, in the computer modules and the graph, and then we're able to make it executable that runs on any robot, any robot. The only thing that needs to be specified for each robot is the different graph, okay, here, and the module limitations. So I think that's a really important point, that we have that we are now able to, in principle, do chemistry on any robot in general. And this is because we can automate the operations, and because we have a universal system, we only need 44 instructions to do any synthesis. And this will be published tonight in Science, but it's embargoed at the moment, so please don't tell anyone until the press release later. I guess hopefully my secret is safe with you for a few hours. But you only need 44 instructions to do any synthesis. So what does this mean? It means with my robot and the software, you can go to any molecule in the literature, take the literature, put it through our system. It will produce a code, a list of reagents to buy. You put the reagents in the robot, put the code in, press run, it will make the molecule. Now, there are a couple of obviously provisos. Not all the literature works because it's not been reported correctly. And there are other hardware problems, reliability with a computer. Remember, I'm an academic trying to prove the principle. I'm trying to prove the principle of the electric car, if you like, not build a Tesla company, but you know what I mean. In principle, now it's a solved problem. All of the literature in batch is accessible. And the way you do it is you go through a synth reader, which has a natural language processor, gives you the procedure. We have a natural language editor that basically helps us interpret the literature, but really it's not the natural language processing. It's the virtual machine that is programmed using our chemical markup language, ChI-DL. ChI-DL is like the program, is like Python, if you like, high-level, human-readable language Obviously, the chemistry language is even higher level, but more ambiguous. KDL makes it less ambiguous. And then in the chemical processor, we then generate the Chem code, which we then compile with a graph and then runs on the robot. A couple of examples here, we've been able to make these, do cross-coupling reactions, make diazarines, and make peptides. And this is on a robot that costs actually probably only 25% of a peptide synthesizer. So most peptide synthesizers cost 100 grand, you know, a pretty good one. And this system here can make any molecule and peptides, and we can basically make this peptide and label it and do some other chemistry all in the same robot. So we're able to converge very different chemistries together using this technique. This is the robotic system to end all other robotic systems. And down here we can see a graph that shows where all the objects are, and this is like the firmware, if you like. It looks complicated, but it's actually pretty simple. I'm just going to show you a little bit of how this works. We're just copying the text now, and here's our app. We just put the text, this is just a front end for the to generate the KDL. Right now it's turning that text into the code, okay, it makes a list. You can look at the KDL code if you want. It also can be error corrected by the chemist. So that means the organic chemist can now check it's correct, make sure there isn't a problem, and then, so because you don't want the machine to just halt and catch fire. So there's, you know, and obviously the literature is not flawless. So we have this kind of error correction tool, which I think is going to help accessibility a lot. Then what you do once you've got your recipe correct, you obviously give it a name. And then you generate a graph, okay, of your procedure. And obviously we have standard graphs. And then what we do is we make sure the graph represents our physical robot. And we then combine the two together. So we compile both the graph and the code. And this is a bit like, you know, taking your Python program or your C++ program and compiling it to work on an x84 processor rather than say on a, you know, on a Mac processor or on an ARM processor. And then at the end, you simulate it to make sure it works properly. And then there you go, fully working system, it will run your computer. As I said, this will be published later today. So why are we interested from a discovery point of view? I want to spend the last 5 to 7 minutes now bringing this all together. I've talked about complexity, how we can go and search for molecules that are special somehow, that are indicators of a design. Now, I'm not a creationist, I'm an evolutionist, and I also believe that the origin of life had something to do with chemistry, but I have no other belief system. So when I'm talking about design, I'm really talking about human beings creating molecules based upon design of experiments they've seen. So please bear that in mind. So what I want to do is say that the computer will open up this whole new world of drug discovery. And the reason is that we don't have that large number of molecules known. It's really a small amount of known knowns. And we need to get to the unknown unknowns. But within 10 steps, there are basically more possible molecules possible than there are atoms in the universe. So we need to figure out how to search chemical space. So how we've been doing this in the lab is we built a robot that does random combinations of taking reagents, randomly mix them together and look at the outcome using infrared and NMR. And what we're able to show using this machine learning system is that after doing about 10% of the reactions, we're able to predict what happens in the remainder 90% of the space and discover some new molecules. This is the setup where we have all the reactors down here and the various pumps and the sensors, the NMR and the mass spec in the fume hood. This is obviously low field NMR, 60 megahertz, so we have a 90 megahertz one, I think. But this is good enough for getting some indication of whether a reaction has occurred. And what we do that is we do a difference spectrum and we look at if there's a difference between the reagents and the product, then a reaction has occurred, and then you can get excited and go searching for that. And what we were able to do is show that the system could discover molecules that hadn't been seen before, okay? And they were quite unusual molecules. You take this molecule down here, or this molecule here, this tetraester. These are all physical molecules made by our robot. But let's go a bit further in the last 5 minutes. Can we really go to discovery? Well, by using a closed loop system and now using a neural net on our NMR, we were able to basically make a model of chemical space and train the neural net to figure out when a reaction is happening. So it was able to abstract the features it would see in an NMR for a reaction process. And we set up a new type of system where the NMR was at the center, because the NMR is a resource limiting constraint. And when I bought this NMR a few years ago, I designed the flow system to go with it. They haven't even thought about doing flow chemistry in this NMR, even though it has a hole all the way through the magnet, which I thought was quite funny. So now we need to combine our chemical language, how to mix, our hardware, how to do all the operations, and then our database and our reactivity analysis together. Now we have a language, and we can write down in English or any language, actually. We can work it in Russian and Chinese, in Mandarin and German at the moment, just because why not? We are able to then generate a library of experiments, like a DOE, a design of experiments, using this approach. And what we were able to do is take this library of molecules using our NMR search, and what we were able to do is find some pretty interesting stuff. So I'm going to ask you, look at this here, this compound Tosmic. Tosmic, we have found to react with diethyl 2-bromomalate, but what happens in DMSO? Can you predict it? Well, I'm 100% sure you can't, unless you've seen the preprint. You get this molecule, of course, this trimer. Well, it looks pretty simple. You can see there's some fragments, related to the starting material. Actually, the bromomalonate doesn't have any role. We've got a crystal structure of it and made a whole library just to prove it works. But here's the mechanism here. But really, I won't bore you with the mechanism because I don't have much time left. I've only got 3 minutes. Is that the mechanism of the reaction is it needed 6 moles of Tosmic. That's 6 moles of the starting material to react. We made 5 new CC bonds. We made sp, sp2, sp, sp3 carbon centers, and we made it in 47% yield. And this molecule was not predictable. That means that no one had ever thought of this molecule before we discovered it. But the irony is, or the exciting thing is, if you get your bottle of Tosmic, if any of you have Tosmic in the lab, just take a sample, put it in the mass spec, and you will see a peak at 693, which shows that one of the main impurities in Tosmic is the 6 fold reaction. There's 6 moles of Tosmic reacting with itself in various ways to produce this trimer. How amazing. And just to confirm how unpredictable it was, we did a Cheminformatics analysis, and we looked at the starting materials and the reaction step, and we basically looked at the proposed reaction mechanism, which is shown here in red, and then lots of possible paths that we generated using reaction smarts, and all predicted paths that you've got, okay? And then once we had the mechanism in here, it really thinned out to basically you're literally getting only 1 in a billion. So really this molecule is a 1 in a billion molecule and not intrinsically predictable from the reagents, which I think will really start to short circuit some organic chemistry brains. Now what we're using is a ChemP used for dyne discovery. That is, we start to have a fitness and reward function. Now we start to make the computational chemist happy, and I say, okay, let's do some proper computational chemistry. Let's generate a library of molecules with properties that we would like, that are known, but we can in silico imagine them. We can solve a Schrodinger equation as best we can, and we then populate a machine learning system to generate new targets that we then do electronic structure calculations. But then, and here's the thing, what we've been able to do, and this is nowhere near published, is we've now got a system that can go from a molecule that we've generated computationally, and it doesn't even need to produce the mechanism, it just produces you the recipe in KDL. So now all you need is a robot, you need a computational system to dream the molecule, then you need a bridge to make the language, the KDL, and then the robot goes and tries and makes it. And that's a really pretty exciting thing where we have really an artificial chemist. And of course, we're applying this to try and make an origin of life machine, and we're calling this thing Alpha Soup Zero. Like AlphaGo Zero, we are going to have to learn the rules of chemistry at the beginning, because the prebiotic chemistry rules are not what we need to crack the origin of life. I'm going to stop here and thank my team who've been brilliant. I want to thank the EPSRC, particular DARPA and ERC, the University of Glasgow. I've now started another spin out called Chemify, which is going to be making computers labeled as Curies. And we're starting to sell them next month, a very limited supply of them. So if you know anyone who's interested and they have a few hundred thousands of pounds available, they should talk to the company. But I also would like to kind of acknowledge that I know the pooling in Scotland has kind of morphed a bit, but it was really the pooling initiative at the beginning that allowed me to get access to a lot of the equipment that allowed me to break the mold as an inorganic chemist and become more of an origin of life, explore new areas. So thank you very much for listening. I'm happy to take questions after the other talk, and I hope I've left the next speaker enough time. Thank you.
Thanks very much, Lee. It was a great talk. And so without further ado, we'll just move on to the next host by Dr. Thomas Label, who is an NMR facility manager at the University of St Andrews. He's managing the entire walk-up automated NMR service there. And he's an expert on various research projects that involve the NMR technology. His latest interest, which we'll be talking about, has been on the data management of high throughput NMR laboratories, which is driving the research project of Nomad, who he will be talking about. So I'll let you give your talk, and as Lee said, we'll take questions afterwards. Thank you.
Okay, so hello everyone. So I hope that you see the slides. Can I just get a thumbs up? That all good. Okay, thanks Alan for introduction and also for invitation. I'm really pleased to give a talk and present my ideas and my work here. So I sort of expected, let's say, general audience here. So I will kickstart with a couple of slides which explain how important NMR spectroscopy is for chemists, and maybe for those who are not chemists out there, so it will make some of the things which Lee presented before a little bit more clear. So what you see on this slide is a molecule of paracetamol, which is a very popular antipyretic drug. So this picture over here shows a molecule of paracetamol, how organic chemists would draw it. So it's a 2D representation of the molecule. So that spinning object over here is a 3D model of the molecule. So that's molecule, if we would see the molecule like that if the atoms would be seen as multicolored balls. So you can see these red balls here, they represent oxygen atoms, and then the blue ball represents a nitrogen atom, and gray balls are carbons and hydrogen atoms in this molecule. So this model here has been produced by some computational methods, but you can see the molecule like that if you do analysis of the molecule by X-ray crystallography. So NMR spectroscopy does not show the molecule like that. So if you, sorry, something happened here. Okay, I'm back again, I hope.
Can't see your screen just yet.
You don't see the screen, or do you see the screen?
Nope.
No, sorry about that, guys. What happened here? Can you see it now?
Yeah, that's it.
Oh, but I shared the main screen. That's stop share. So
you need to share the PowerPoint first, and then start the presentation.
So I have started the presentation. Oh, this is. Share screen. I don't see it.
Just start the presentation.
Yeah, I've started the presentation.
Start the slideshow at the bottom. Keep it shared and start the slideshow after you've started sharing. So share PowerPoint as an application first, like you did.
Okay. So now I just can't see the Zoom.
If you just share your screen again, and when
share screen. Okay, so
PowerPoint is up and shared.
Share. Okay.
It's down to the bottom right. You can hit the icon that starts the presentation.
So I started the presentation, but it does not really start the presentation as I
press F5.
F5.
You have to jump to the next. Oh.
So you probably just see the small screen, is it right? So you just don't see, you see.
That's okay. If you go into display settings.
No, what you do, display settings and just switch over the views. So click on display settings.
Display settings.
Yeah, click on there where the display settings is there.
Yeah.
And then just quick swap. No, don't. That's it. That's what swap, present, and view. And there you go.
There you go.
Okay, thank
Thanks,
you.
Lee.
Thank you. Okay, so I was talking about so the NMR spectrum. So you don't see the molecule like that by NMR spectrum. So what you see instead is this chart here, and you can see it like a fingerprint of the molecule. But one big difference that if you have a fingerprint, you can't really say what the person behind the fingerprint looks like. But with NMR, you can actually say or convert the molecular structure or identify a molecule in a pure form or in a mixture. So what I'm trying to say here, or I will try to sort of explain what I mean by that in this very quick example. So in this molecule, you can see 5 different environments of hydrogen atoms, and you can see 5 different peaks in this spectrum. And you can use some information in the spectrum to assign the environment. So you have a couple of information like the intensity of the peak, position of the peak in the spectrum, and also find pattern of the signals, and you can make the assignment here. So on this slide, I would like to compare these 2 methods. So the X-ray crystallography and NMR spectroscopy are sort of key analytical techniques for chemistry these days. There's obviously some other techniques, but these are sort of really key methodologies that chemists use to identify molecules. So I will sort of try to do a bit of a comparison here. So let's have a look on a sample first. So for X-ray crystallography, you have to provide a pure sample in the form of a single crystal. For NMR, you do you can prepare a solution, or you can use a powder material in pure form or a mixture. When it comes to the experimental time, so X-ray crystallography needs a couple of hours or even days to do the analysis. For NMR, you need minutes or hours, depends on the complexity of the problem you want to solve. So X-ray crystallography is usually used as an ultimate proof of molecular structure. So what I mean by that, so if you are a synthetic chemist and you work on a certain synthetic pathway and you want to prove to the world that you actually made something, then you need to make, or you usually provide X-ray crystallography data to prove that you have done that. So on the other hand, NMR spectroscopy is used for, on daily basis, a quick analysis of substances. And another difference is that X-ray crystallography is practically one experimental method, but NMR spectroscopy use loads of various experimental methods. So we can look at different atomic nuclei, we can do some multidimensional correlation techniques, and so on and so on. The other difference is a format for data deposition. So X-ray crystallography has, from a early beginning, well-defined format for data deposition, which is called CIF, Crystallography Information File. And on the other hand, NMR spectroscopy does not have that file. And that sort of propagates into the fact that X-ray crystallography, if you want to find some X-ray crystallography data, you can go to CCDC, which is Cambridge Crystallography Data Center, where you can practically find any crystallographic data which have been sort of acquired since the dawn of the technique, but NMR spectroscopy does not have anything like that. So there is quite a burning question at the moment in the NMR community, which basically asks why there is not an equivalent of CCDC for NMR spectroscopy, why there is not like a Google for NMR data when chemists could go and basically find the information. So there are some sort of ideas about that. So some people in the NMR community say that it's the missing format. So there are sort of initiatives we try to sort of define this format. So there's an academic initiative which is called NMR e-data, and there is also sort of movement driven by pharmaceutical industry, which is called allotrope. But I personally think that the difference or the reason for this stems from something else. I think it has something to do with the workflow which we sort of have in the NMR labs. So I have here example of the workflow from the 90s when I sort of started to do NMR. So everything starts in the synthetic lab where you have a synthetic chemist who makes something. He does not know what it is, so he makes a sample. He goes downstairs to the basement to see another scientist who sits at the very sort of weird instrument, which is like a combination of a very powerful magnet and radio. So that guy pops the sample into the magnet and acquires an NMR spectrum and interprets the NMR spectrum, then goes to see the guy in the synthetic lab. And the guy in the synthetic lab looks at the result, and he can do two different things. He can either file it if he thinks that this, is something what he wanted to make. He's happy with the result, so he files it. And if it's something which he does not like, he just bins it. And the guy in the NMR lab can also store the data in a floppy drive like this to print the data later if the synthetic chemist comes back that he lost the data. So back in time when I started with NMR in the 90s, I would do maybe about 10 to 20 experiments per day. So what is the situation today? So in 2016, I made a survey among my colleagues in academia, so to find out what we are actually doing in the NMR labs. So most of the labs in British academia, they support synthetic chemistry. Most of them, they do some other chemistry niches, but the sort of core of the NMR work is done in the synthetic chemistry. So I try to make a picture of average NMR lab in UK academia, and it's about 6 instruments, where about 4 of the instruments is equipped with automatic sample changer. So these automatic sample changer can ramp up the productivity quite a lot. So we can basically work 24/7. We have about 150 users in average, and we can do about 4,000 to 400 NMR experiments per month. So for comparison, you can see some data from St. Andrews, which are sort of slightly above average. So let's have a look on that workflow a little bit more in detail. So what is happening in the NMR lab in these days? So first of all, we have these automatic sample changes. They are great, so we can operate 24/7, and we can have really, really high throughput and generate thousands of NMR data every month. So what is happening with the data? So mostly the data are stored on network shared drive without any search facility. So just basically the instrument dumps the data in some sort of complicated folder structure, and users usually sort of retrieve the data immediately as soon as the experiment is finished, because finding something in that sort of heap of data is really, really difficult. It's like looking for a needle in the haystack. So the other thing which is happening here is I call it pyramid of users. So at the bottom of the pyramid, we have students and postdocs. So these guys, they do the work. They are the synthetic chemists in the lab. So they make these molecules. They sort of submit the samples for the analysis, and they look at the data. So if they, at the end of the day, they sort of write some reports and pass it to the PIs. So the PIs usually don't look at the NMR data. They usually just look on the report which are provided by postdocs and students. And then on the top of the pyramid is the NMR expert. And the NMR expert these days just gets to see a very small fraction of the NMR data. So the usual scenario is following that, the PIs don't understand what is happening. They go to see the NMR expert, and the NMR expert looks at the picture that they usually print out, and the NMR expert says, like I can't really help you with that unless you give me the original data. But the PI say, well, we have done it a couple of years ago, and the student left, and can you find the data? And the NMR manager says, like, well, can you give me some sort of idea where the data could be? Do you have a data set name or something like that? And they usually don't have it. So then they end up by either sort of finding the molecule somewhere in the cupboard and running the spectra again, or doing the synthesis again. So I have here another sort of question for the NMR community. Who is going to do that NMR data deposition if we define that common format? So the NMR expert is going to see only a small fraction of the data, so he can't really deposit everything. The PIs usually don't bother to use NMR software, so they won't do it either. And students and postdocs are very unreliable and elusive, and they usually try to avoid any extra work. So it's really a sort of slim chance that we can sort of create the depository that way. So what I'm actually trying to do with Nomad, so I will try to explain it using analogy with digital photography. So back in the 90s, we have these fantastic point shooters which had resolution about 1 megapixel or 2 megapixels, and then we stored the data on these memory cards. And if you wanted to have a look on the pictures, then you would either connect the camera directly to the computer, or you would take the memory card and put it in the card reader, and then you would print the pictures on a printer to show it to your, let's say, friends or parents. So what we are doing these days, so we use mobile phones rather than these point shooters, because on the mobile phone you can have a really fantastic camera with AI and stuff like that. And then we have these cloud platforms like Google Photos, which automatically acquire the picture that you take, and then with the push of the button, either from the Google Photos or directly from the phone, you can share the pictures on the social media. So what I'm trying to say here is that that what we do with NMR data these days is practically what we did with the digital photography in the 90s. And what I try to do with Nomad is basically shifting everything from 90s to the current days. So this is like an overall scheme of Nomad. So by the way, Nomad stands for NMR Online Management and Data Store. So we use these sort of acronyms in NMR quite a lot to name experiments. So I use the same here, and I sort of tried to market it a few years ago, like smart and complete solution for NMR laboratory data management. And you can sort of see it like 3 pieces of the whole system. So the first piece is the control piece. You can see it like a software on your camera. So it's like a centralized dashboard for NMR administrators or NMR management to control the traffic in the lab. It generates usage statistic, user management. You can sort of remotely control and monitor the instruments. Then so you might think that this sort of control piece is not really important for the data management, but there are sort of 2 things which I would like to point out. One thing is the user management. So these days you have hundreds of people coming into the lab, and if you want to organize the data in the database and sort of connect the data with the provenance metadata, you need to have that user management, which is provided by this control module. And then the other thing is this control piece provides a lot of utility for NMR managers. And these guys are very sort of important players in the whole sort of business, because they have a lot to say about what is going to happen in the NMR lab, and what software is used and what machines are running there. And if there is a lot of utility which the system provides, they will be more sort of happy to put some effort into introducing the system into the lab. So the second piece, the database, is something like it's the Google photo piece. So it automatically acquires the data from the instrument and stores that in the database. So we have basically a combination of raw data with provenance metadata, and there's also a lot of tools for annotating, editing, and sharing the data between the users. And the last piece, the purple piece, open access data, that's basically the social media platforms, sort of, where you can sort of share the data between other people within the community. And I sort of have a vision of some sort of decentralized repository which will be driven by the community rather than a centralized service running by the company. But I will come back to that point a little bit later. So the whole system is actually sort of created by two apps by chance. So the way how it sort of things evolve. So the version 1 was developed between 2012 and 2016. So most of the functions have been deprecated, but we still use it for controlling the instruments. And version 2, which was developed between 2016 and 2019, does mainly the database sort of piece. So this is sort of more looking under the hood of the whole system. So as you can see, we have 6 NMR instruments in the lab, and they are all sort of controlled by Nomad systems. So to understand that a little bit better, so that obviously the acquisition of the NMR data is controlled by the vendor software, but our users don't interact with the vendor software. They come and use our sort of, we call it submission portal. So that is sort of replicated on many computers and all synchronized. So they can come into the lab and basically pick the nearest computer and decide what they are going to do in the lab and submit the samples. Then the database piece actually acquires all the automated data and also the data which we generate on the instrument if we do something manually. So sometimes we take the instrument out of the automation and run some experiments manually. So all the data is acquired in the database. And obviously the database provides a lot of search facilities. So you can search the data using some sort of metadata, but we also provide functions for, let's say, reorganizing the data. So to understand that, you need to sort of see a little bit more how the chemists analyze the molecules. They usually don't analyze everything in one go. So they do really, really quick analysis of, let's say, during the day. And then if they see that the sample is good, they run some experiments during the night, and later on they can come to see me, and I will say, well, you need to run this and that to make the full analysis. So at the end of the day, the data associated with one substance or one compound can be scattered across the database. So I basically give them a functionality to put data together into containers and then put some more sort of metadata on the top of it, which one of them is a molecular structure. So that 2D sort of representation of the molecular structure, and that enables us to search the data by molecular structures. So we have also tools for viewing the data. So you can actually display the data on the platform in the browser, but it's not just looking at the picture, it's actually interactive viewer. So there's data visualization that you can actually expand bits of the spectrum and look sort of deeper in the spectrum and analyze it. And then there are also tools for sharing. So you can generate a link and pass the link to a compound or project to your postdoc or to the supervisor. So these are the two pieces over here. Nomad Nmr Analysis tool is like extension of our viewer. So we basically try to add the functions on the viewer, which allows us to do integration and peak picking, some basic sort of NMR processing functions, which allows us to analyze data. And we also try to run MNOVA processing software on the server and talk to the API of the software to do some automatic processing and analysis. So both these two pieces, they were sort of developed by students who left, and we never managed to get these into production, unfortunately. So, and then the last piece, as I said many times, is just a vision. And the idea is that if people work on a project, they can put all the sort of data associated with the project into one big container. And once they are finished and they are going to publish the data, they can just basically with a very easy push button, push it in the platform, which is accessible from outside of the institution and then will give back on return a DOI number, which they can stick into the publication. And obviously that platform would provide some additional tools like what we have already on the platform inside. So that would be like search, analysis, and also tools for commenting and voting on the data. So that's very sort of the idea which I took from Stack Overflow, so that the users could upvote or downvote the quality of the data provided by other users on the platform. So I will sort of try to evolve a little bit more on my vision of NMR depository architecture. So there are already some centralized generic research data depositories, and NMR community sort of says, okay, we define the format, and then we will publish the data on these generic research data repositories. But I have a couple of problems with that. So first of all, these generic data repositories do not provide any tools or utilities for NMR data analysis. So you can't really search by sort of, let's say, NMR parameters or by molecular structures. It's just basically gray containers, which basically can't be really properly searched. And also, these are run some institutions or companies, and they have a central point of failure. So I sort of see them like unsustainable solution. So what is my vision? So I have a more sort of a vision of a decentralized system. So what do I mean by that? I don't want to say here that Nomad is going to rule world. So there's a lot of discussion in NMR community about NMR data management, and we can envisage that there will be some other sort of platforms happening in future in the world. But if we have these local NMR data management systems, they can share resources to create P2P network of nodes. So that means that the participants in the network can receive the content, but they would need to also host the content. So the storing and sharing of the data would be facilitated by common protocol, such as interplanetary file system, which I have here as an example, but it could be something else, because there is quite a lot of happening in this sort of in the world of decentralized applications. So there might be something else emerging at some point, and which might be better than what I have over here. So, and I think that this sort of decentralized solution would be more sustainable than a centralized solution. So my message to the NMR community is that basically we should, rather than talking about the common file format, we should talk about peer-to-peer protocol. So now let's have a look on some other things. So you might have a feeling that I have already prototype, and I should sort of share with the NMR community and move to the sort of second phase and start to work with the decentralized platform. But the problem is, I have a problem with the whole project, which stems from a couple of things. It's just team, technology, and funding. So the first of all, let's talk about the team. So somebody said that Nomad has been built by children without any supervision, which is really bitter words, but very, very true. And you sort of need to understand how the Nomad was built. So it was basically built by students without any supervision. And the other thing is the technology. So we moved the technology from 1998 roughly to 2008. And the last thing is the funding. So at the moment there is no funding, and I don't really see any funding coming from somewhere soon. So in my last slide, I will just sort of try to talk about the So I will try to talk about if there's any future perspective of this project. So if I have any thoughts about the Nomad version 3, because I was basically discontinued the development of version 1 and version 2. So I had a couple of ideas about it, and I realized that I would basically, if I would want to sort of move this forward, I would need to find a developer who would be able to sort of work with me. But these developers are very difficult to get, especially if you don't have any funding. So therefore, I've decided that I would sort of start to learn JavaScript, and I started about 2 years ago, and after about 1 year, I became a little bit more confident, and then I started to research some more advanced technologies, and basically got all these technologies under my belt. I can't really say that I'm proficient in these technologies, but I started to use them to build some pieces of Nomad. And if you want to see what I have been doing recently, so you can have a look on my GitHub, and you can see there are 3 repositories at the moment, which are sort of beginning of the Nomad version 3. So Nomad control dash is a part which that's basically a front end of Nomad 3, which I have been building. Then Nomad Nmr control client is a code which I entered to run on the spectrometer, which should provide the data for the server, and Nmr control server is a code for the server. And if you are not a developer and you can't read the JavaScript code, then you can have a look on this link over here, where I host the front end demo at the moment. So okay, so that's it. So thank you very much for your attention.
Okay, obviously the weird thing of online conferences, there's no clap at the end of the talks. So just I'll thank Thomas and Lee for their talk. I'll ask Lee to share his screen as we move on to share his video, and unmute his microphone as we move on to the questions. I've received a couple of questions from the portal. Don't forget to send stuff through either the portal or the chat function on Zoom. So moving on first for a question for Lee. So there was James Gumby, who says that he enjoyed your talk, and he was wondering whether or not you explored how your molecular complexity measure compares to crystallographic complexity, i.e. the entropy based on symmetry, and how they correlate, or if they correlate at all.
So there isn't really an entropy based measure for crystallography. You can look at how complex a crystal structure is by looking at its CIF file and looking at some mutual information measure. But the problem is you have to put information in. So this is the first time ever a intrinsic complexity has ever been measurable, right? And the assembly theory is quite deep. Now we are applying assembly theory, not to molecules, but to crystal structures. And that's in progress, so it's a good point. And does it work for crystal structures? Yes, it does. Does it correlate what you expect with symmetry? Yes. But the nice thing is you don't need to have any information about the identity of the structure. That's really important, because otherwise you're adding information in. And so the problem I'm working with a couple of interesting cheminformaticians playing with mineral complexity. And it's a very difficult thing, because you have to make sure that you're using the same basis set to quantify the number. But yeah, but basically the more unsymmetrical you make something, the higher the information content, right? The trick is when something becomes super unsymmetrical, in the limit, it looks as complex, or there are as many as 3 variables there are in the say, let's just say take a tray of sand with lots of sand grains. If each sand grain had a different kind of registry, so it looked random, but you could generate that precisely with a piece of information, then you've got to work out how to tell the difference between the random ensemble and the complex ensemble. And this is one of the big holy grails in complexity science, which assembly theory actually solves. So watch this space. And certainly I came at this from the crystallographic point, making polyoxymetallates that were more and more unsymmetrical, and trying to work out how much information I could put in to desymmetrize them. So it's a really nice question. Thanks very much.
We then have a question from Timothy Storr, who asked a question to both speakers, and saying he's making the comment generally, or question from the software engineering rather than computer science perspective, and whether or not both visions of these talks bear a strong resemblance to DevOps and infrastructure as code trends in the software world. So whether or not the speakers are familiar with the state of the art in this world, and if they know, if they have a view on their work and how it relates to that. For example, Lee's programming language, KDL, and it bears a resemblance to the purpose of languages for developing virtual machines and networks. And saying the software engineering research community is beginning to explore how these tools are being used in practice, and the problems and disadvantages that are starting to arise from that. So wondering about that interaction between basically software engineering and the work that you are doing. So who wants to take it first?
I can say, so then maybe Thomas might say something from his stuff. So we're using some parallels to software development, but really what we've got to do here is you go way back to when the first computers were built. The computers came first, and then the operating systems, and the software, and then the collaborative tools. One of the reasons why chemistry hasn't been digitized until now is because everyone tried to make the software first, and no one had the tools, the hardware, so no one used them. And so this is always a big problem, right? So what I wanted to do is build a system, then an architecture, which would be cheap enough for people to use, and then develop software on that. So, and that then has to integrate a lot of existing tools. So a lot of existing kind of approaches that people have out there we're using in our system, but there is a kind of, it's not the same as software development, it's more hybrid. And because this is not just virtual, it's real, right? The software is not running on a computer, it's running on a physical machine that will be causing things to happen. So the kind of traceability problems you have, say, with automated cars, you're going to have in the computer software stack, if you like. I can explain a little bit more, but I mean, I wrote the programming language years ago, actually, when there was no robot, and my group told me to piss off. So I then built the robot, and then said, let's use the programming language, and we've been using development tools, and also agile development tools there. But let me hand over to Thomas.
Yeah, so what I can say here is that that sort of software engineering was really a big pitfall for the first versions of Nomad. So I wanted to sort of talk about it a little bit more on that slide, but I thought that I'm running out of time, sort of panicked, and I sort of skip it. So you sort of need to understand how I got into the whole sort of Nomad development. So it started in 2012, and I had absolutely no ambitions to do any sort of software development, and so just some bosses turn up into my office, and they said, like, we got some grant money here, and you can have a developer to work with you for 6 months, and try to do something about data management here. So we did, and for 6 months we worked together, and I really was sort of just throwing ideas in, and he did that sort of engineering implementation, and he used some technologies he was using in his previous employment. So he used things which were not really up for scratch. So he just basically used what he knew to do, and it basically created a status quo, which basically was followed by the other students, and that sort of created a big hurdle. Then I was sort of presenting the system to the NMR community, and I got really, really good feedback. So there are a lot of people came back to me and, can I have it? Can I run this in my lab? And I said, oh, okay, we will give it a try. But as soon as we tried, and we started to sort of reach the hurdles, and we really, really struggled. So therefore, when I sort of decided that I have to give up, that the back is really, really heavy, then So I decided that I sort of need to learn myself, and I started to sort of look and learn what sort of technologies are used for building the interactive web apps like Nomad is, and made the choice for the JavaScript, and then sort of started to explore the sort of more advanced libraries, and end up with the Nmr stack, and I think that's the way forward. And I think that it will sort of, if I will ever manage to put together something meaningful, that it will make sort of sort of progression much sort of better and easier to implement it in some other places.
I mean, one thing to also add to Thomas, I mean, one of the problems that Thomas has got with the NMR stuff compared to CIF files, it's a really good comparison, is that although each CIF file is individual from the data collected, whether you've got the HKL file in it, normally it's intrinsic. The problem with an NMR sample and an NMR spectrum is not intrinsic, right? Anyone can put any old garbage in an NMR tube and run it. And so one of the things I'm doing in my lab when I was in contact Thomas is that with our computer, with a programming language of KDL, we're also making a Chem coin or a proof of synthesis, because people can start to share KDLs. And then how do you know it's not made up? Yeah, now, okay, you can generate the NMR and generate the mass spec and generate stuff, but no, there's a way where you can take the carryover in the NMR to take the entropy in the NMR, or not the entropy, the actual byproducts that are carried through the process, use that as a fingerprint to know that that NMR is associated. When you then start to do things more robotically, then you can have a better trust network going back. So one of the things I think Thomas's stuff is ahead of its time. It's brilliant, but I think during the next 5 years, he's going to find it really interesting because there can be context given to the NMRs to say, oh, this program, this code generated this sample, which gave this FID. And I really would like to label the FID with an encryption key that connects it back to the method of production. Then Thomas, as an NMR spectroscopist, doesn't have to say, did you just TIP-X out the peak? Or did you manipulate it's like, how do you connect the data securely? And I know that's going outside the question about the software tools, but I think it's quite an important thing to bear in mind.
Yeah, so this is really valid comment. I sort of really welcome that, because obviously, my head is spinning around this as well, because, people can just submit to the repository practically anything. And then there is a question, is it really valid? Is it really true representation of the compound? And therefore I came with the sort of idea of voting and which you can see like in the Stack Overflow, that you can basically say, oh, this is actually good data. This is very well, presented and interpreted data. And also the sort of, certification with some sort of key. You have sort of proof of origin where it's coming from, and then nobody can sort of falsify it. But
when you have large data like that, data validation is always an issue. But it leads us a little bit to the following question to Lee from Oana Andre, who's asking, how do you ensure that, first question, how do you ensure that two different types of robots are going to produce the same results with your language?
Oh, well, that's simple. The language doesn't have anything to do with it. It's a bit like saying, how can you be sure the same app is going to run on two different processors, say a Google Android, right, processor system, and say a different type, a Microsoft one or an ARM one. But let's talk about the hardware. So what you're saying is like, so that's two different robots, two different hardwares. What each robot will have is, because our virtual machine can simulate what's going to happen, each robot has to live up to a certain specification. So the robot has to tell us what the module capabilities are. And then basically in our compilation, because we have the graph and we know the module capabilities, we can simulate it and it will either work or not. If it passes the simulation, like you just check it for bugs, then we will be sure it works. Now, whether there's more variation, okay, or more impurities, or maybe other things that come in that lower yields, that's also, going to come in, because there are things like the robot can get cold. Let's just say a human being would do something hot chemistry-wise and pour it, whereas if you're pumping it along a really long tube and it gets cold, then obviously you might precipitate your material and just break the robot. So there are very interesting technical constraints as this comes away, but the way I would look at it is a bit like the language compiles to any robot. The robot must have fit the standard. So one of the things I'm doing is the KDL, you should think like HTML. KDL is a new standard to express chemical synthesis and later analytical data, and they'll be locked together. And then we need to make sure the robots are up to running that KDL, and that will be a separate validation routine. But the most exciting thing is if you've got an old ChemSpeed robot or any other robot you want to design in your lab, do your means, as long as it fits the module specification, it will work. And that changes everything.
Mm-hmm. Okay. There's a second question from Owana, who's asking, can you ensure that some bad pathways are not taken forward just as much as some bad molecules or projects are not obtained during a procedure?
Yeah, well, that's really much the beginning. So Google's just given me a load of money to do that, right? Basically, start to generate an infinite library of KDLs and run them and see which ones are good and which ones are bad, and how. And there's so much optimization that can be done. It's like route planning, but not virtual route planning like Chematica or something, but real route planning where we actually physically go to the destination and check it's there. So a lot of this is going to be happening, and then it's just the beginning, right? There are 12 computers in my lab. There's one in Berlin, one in GSK, and there's soon to be 2 more in the US. Once the number of computers or the number of people using the kind of the CPU, the ChemPU standard that is run by KDL, suddenly this will all take off and we can ask those questions, and I would be really excited about asking them. But it's a good point to start thinking about them now, thinking about variability, cost. You know, there are some, the literature out there is notorious, right? Chemist goes away for lunch, experiment takes over lunchtime. Why is it why is it being left in the literature for 12 hours? Well, because it was overnight. And now you've got your robot running, you can question all those time parameters and the variability of the temperature and so on, or the rates of addition. So really, we need to reinvent all of synthetic chemistry.
Mm-hmm. I think from a chemistry side of things, obviously one thing that has to go alongside with that is better integrated analytics to see what's going on within your reaction, to be able to make those decisions of actually you input into your computer, I want A, and you have something analytics to say, well, even though it says that it should be run for 12 hours, I actually see that I've got A and I'm starting to make something I didn't want. And therefore I'm going to stop the reaction now.
Yeah.
Is that something you're trying to input into your work?
Yeah, that's next year's science paper or next month's science paper. So we have an optimizer built in. So the number of sensors we have on the system, we have what I would call passive sensors, which are just to check the robot's working. RGB, so touch, basically the basic, so we've got vision, electric field, okay, and looking at the infrared or something like this, so some molecular property, and that's really cheap and easy to do. What we also have, as you might have seen, we have benchtop NMRs and mass specs, but they're very expensive. But there is another technique we've developed, which is I'm patenting right now, which will allow us to give all of that on the benchtop for basically less than $20. So we have a real-time analysis process that costs $20 for the hardware, and we'll put on all the computers. And it's not going to be as good as high-field NMR. Thomas is still going to be very much in demand, but it's just about basically checking you're roughly on the right track so you can optimize where you are, okay? And I would look at it like the automated car roadmap. What we've started with the robot is we take out some of the manual labor. The next step is to go semi-automatic and increase the autonomy so you can leave the computer running and the computer can fault correct. And even if a pump fails, that we have an automatic rerouting routine where it brings another one, like a redundant engine in an aircraft, right? Or a redundant system. And that's very important to have those kind of things in mind, but that's coming.
Okay. There's a question for both speakers. How do you see your work influencing computer science or software engineering research? Obviously, you're very much aligning with chemistry, but in the session, we wanted to really see the interaction between computer science and chemistry. And how do you see that your work is influencing computer science in its own right?
I can answer that quickly. I could give a different lecture. I've made a chemical computer that basically beats a mainframe at solving a simulated annealing problem, but that's funded by DARPA. So we've actually made a chemical computer that does an analog computation encoded. That's coming out in a couple of months. I'm having a bit of a fight with a certain journal at the moment about it, but basically the idea is that the matrix inversion is not done in the computer memory, it's done actually in the chemistry, and we can do annealing, numerical partitioning. So we're going to rewrite computer science, because computer science is fictitious to some degree, right? It's based on the von Neumann machine, or not fictitious, it's very limited on this system. There are other ways to do computation. So what I'm really excited about in interacting with computer science is actually this interface, this hybrid interface. In the same way quantum computing requires a digital computer control it, what would a chemical computer use on the chemical side? Let's now go to the synthesis. How can the computer scientists use synthesis robots to think differently about how they do their research and how that would get them to think differently? Well, it's about embodying or outsourcing the calculations to real experiments. A lot of computer scientists that work with physicists, chemists, engineers are doing calculations. What if the calculation is done in the real system and you're just reading it out and populating a database? So I think the computer science is a really exciting place to be. One of the things I would like to do is get more computer scientists into my laboratory, not scared of chemistry. And I'd also like to get more chemists in my laboratory, more used to doing mathematics, applied mathematics, which will turn them into very useful computer scientists. But I'm sure Thomas will have a view on how to get more computer scientists into the NMR lab.
Yeah. So what I would say about that. So at the current stage, it's me more sort of exploiting computer science rather than sort of bringing something into the computer science. So everything what I have found so far when I sort of started my JavaScript journeys, all that sort of these sort of advanced libraries is just a sort of amazing piece of technology which sort of helps to build the things like Nomad really relatively quickly. So this is, at the moment it's more exploitation rather than providing something back. So once, if I will ever manage to build something meaningful and will have it running in other labs, then sort of I would really love to move and experiment with these sort of decentralized protocols. And I think then that could be a good sort of playground for people in computer science who are actually playing with these decentralized technologies, because I think that they might be looking for like real life implementation of decentralized protocols. And I think the NMR could be a place where they could actually find themselves and really help. So that's my point of view.
Okay, thank you for that. Just one final question before we move on to maybe a more open-ended question to finish with the session. Question for Lee from Tim, who's wondering about the readability of experiments in your KDL notation. Does your group explore some other semi-structured representations, such as gherking?
No, I don't know what that is. No, we don't need to. We just convert it back into English or to German or to whatever. It's not about, so the representation is not important. So, I mean, maybe if you tell me what that representation is, I can maybe think about it. What is important is actually the hardware link, the hard link between, so a couple of things that needed to make this chemical processing unit possible was the recognition that we needed to do batch chemistry. And if we did batch chemistry, we could use the concept of shift registers and state machines. So then when you have state machines, then the representation going up to there. But at the moment, the chemist will write in English or whatever language you want. Then our system will then turn it into KDL, but the KDL is broken into steps, which is very, very readable. It's an extended markup language anyway. It just happens to be a chemical extended markup language here. But I'm sure you can make it interoperable, into convertible in any other kind of representation, as long as it makes sense. The main thing is how to not scare the chemist, how to make sure it's structured correctly so we can then run the machine. And I just build it, like I said, from a chemist knowing about the computer hardware. I remember I designed computers before I became a chemist in my spare time. And that kind of, well, I was an amateur, and that amateur knowledge of how microprocessors worked really, really controlled how I designed the language, so I could make compilation easy. And that might mean it looks a bit silly, right? I might have reinvented the wheel, but it seems to be okay.
Okay. So I think just to finish, we'll have maybe a more open conversation about just generally trying to wrap up and bring together. So we've got some chemistry experts and we've got some computer science experts in the call to say what potential challenges, or what do you see as potential outcomes of the interaction between computer science and chemistry? What are some of the questions that potentially, you know, tickle your imagination of things that you think maybe have not yet been probed and have a value in their own right? So if people from the, I do believe that people from the call are able to join in the discussion, but I'll start opening that from maybe from Lee, and to see if he has any thoughts on that.
So one thing I've done for fun is I'm making a new type of computer processor called a brain gel, which is a neuromorphic chemical processor which is not instantiated in silicon. And I want to go for AGI. And one of the interesting things about this artificial general intelligence is we've got this chemical brain and we're training it, the neural net, in a simulation, right? So the simulation of the world is is giving information to a physical chemical system that is being programmed by the simulation. I think that's a hilarious philosophical argument, because although we probably don't exist in a simulation, Elon Musk thinks we do, the first AGI that I try to make, or the first chemical consciousness I try and make outside of biology, will be trained in a simulation, because I don't have the money to build a little robot chassis and for it to wander around and kill things and do bad things. So it would be interesting for computers, the people here, to think about the role of simulation, not just in the role of simulating reality, but chemical reality, and also how the new techniques that have been brought in machine learning and other data processing techniques might be used in the chemical sciences and vice versa. Equally, you might think what I'm talking about is just completely crazy, and you're right. I'm getting loads of money to do it, though.
Yeah, you might as well do something crazy, right? So I'm just wondering if anybody wants to raise their hand or add a comment to that. One of the things that, you know, trying to organize this event that we spoke about with SICSA, we did wonder about, you know, that there's growing interaction of the work in computer science of the human computer interaction, and I do believe that there can be some interesting new avenues to look at in terms of how a computer or potentially an AI can interact with a chemist. I just wonder whether or not there's any thoughts on that. Trying to keep track of the questions in the Zoom portal as well. Obviously, the other part of, you know, we're talking computer science, something that Lee touched upon, you know, different types of programming languages. I believe KDL is one of those ideas, to invent a new type of programming language that helps to link up the two together. I think, obviously, in the sense of when you look at what you were talking about, Lee, and you look at the reproducibility of different experiments and how you're trying to use robotization in order to influence that, I wonder whether or not how much of the other types of monitoring of the scientist could happen, you know, without having to resort to a robot, but how much monitoring of the scientist can happen in order to maybe try and capture what the scientists are doing and transfer that into a written program of what's happening. Apologies for the children in the background.
No, that's okay. A good part of the world. Look, I think there is so we have not to give away too many secrets, we're also making a computer for nuclear reactors and for radioactive labeling. And in that case, you really want to be able to say, like, I don't know if you imagine Minority Report, where you want to be actually have fingertip recognition, and for the computer to be able to translate what you're doing with your hands and translate it into computer cognition. And we have a process for doing that at the moment that we're playing with. And it's working pretty well, actually. But the KDL actually means you don't really need, you could think about it, but if you can write it down in English and then convert it into KDL, and you're just writing and you're actually describing precisely what you're doing, you don't really need it. And we've also got a project going on called Chemify 100, where we're taking the top 100 molecules and we're making them in a computer and generating all the KDL and showing they work. And we're about halfway through, and the computer just keeps working and working and working. Remember, guys, when I first invented this, all the organic chemists in the world said this is impossible. It will not work. We do magic. And it's my faith in the scientific method and no magic. What they meant is what they were doing was relatively undocumented, and there were secrets. About reproducibility. So I don't know if there are any organic chemists here who would like to argue with me, but I always found it funny, the organic chemists, particularly the older ones, just said, what you're doing is impossible. And I'm like, all right then, cool.
Thomas, you've got your hand raised?
Yeah, just one thing sort of flicked through my mind. So another sort of opportunity for the computer science to sort of contribute to NMR these days. So obviously the interpretation of NMR is really sort of complex process, and so there are sort of tendencies to sort of automatize it, and my sort of effort for collecting the data sort of should contribute to that, because if you want to sort of develop some sort of AI which would be able to interpret the NMR, would need to have some sort of data feed which would come from.
We've already done that.
You've done that.
We have a system that can predict any molecular structure from any NMR. It's not perfect. It's about 95%. I can show you it, Thomas, if you want.
Okay, yeah.
It uses deep learning, but it's kind of boring because it's machine learning. Machine learning is boring, right? Because if I want to do an NMR, I wouldn't give it to machine learning. I'll give it to Thomas and say, can you help me figure out what that multiple's doing? I mean, it's just for nonlinear regression. I think AI is oversold, overhyped, and over nonsense.
Okay, fair enough.
I wonder what the reply from the computer scientist would be here. Obviously, as I said, if you're wanting to participate
I'll try to get
with your microphone, please do raise a hand and we'll enable your microphone. We only have a few minutes left, but some interesting questions being raised here, obviously.
For fun, if you take I'm taking different kind of AIs and letting them converse with one another. And it's quite funny. If you want to do it, you should get Siri, Alexa, and Google and put them in a triangle and get them to talk to each other.
That's the low budget way of doing it.
It's okay. And also, if you want to break the GPT-3 algorithm, that's pretty interesting. If people, when you get phoned up saying you've been in an accident, what I started doing is say, oh yeah, which one? And the AI is not expecting you to say which one, and they hang up on you.
It doesn't seem like there's much activity in requesting to engage with the conversation here, and I can't see any more questions up on the chat. I think just in closing remarks, I want to thank Lee and Thomas for their contribution. Obviously, it's great to hear what different parts of research science you're exploring for answering some of the questions that exist in chemistry with its interaction with computer science. The idea that we have in ScotCHEM was we would like to hear from people who have participated in this session, who may have additional interest in interacting at that interface between computer science and chemistry. If you're interested, please contact us. Either contact your SICSA representative or myself. Because we really want to try and get people who want to look at those interesting ideas together in a room, look at the unknown unknowns, look at these things that people not necessarily have thought about, but whilst really trying to promote both sciences in their own right. We don't want chemistry to be to be used by computer science, and we don't want computer science to just be used by chemistry. The idea is really to try and promote science in its own right by using both sets of experts. So just in finishing again, just thank you, Lee. Thank you, Thomas. And if you have any questions, feel free to contact us at any time. And thank you very much.
You can email me if you've got questions as well. And Thomas, I'll catch up. I really enjoyed your talk.
Okay, thank you very much. Thanks,
Alan, for organising.
No problem.
Right.
Thank you.
Okay, thank
See
you
you later,
very much.
everyone.
Yeah.
Take care.
Okay, bye-bye.